standard access control lists only permit or deny traffic based upon the IP address, the source IP address. There is another kind of access control list that's more has more features called extended access control list, but they're not a topic for this particular one. We'll see that in a later course. Okay, so access control lists, there's a two-step process. We're going to make up a list of permit and deny statements that say what IP addresses are permitted, what IP addresses are to be denied, and then we're going to apply them to one of the ports on the router in an inbound or outbound direction. So the standard access control lists that we are going to use are just the source address of the packet. The device that created the packet, he signs it with the source address. He then addresses it to a destination device. We're just going to look at standard access control list in this particular 8 weeks. We're just going to look at the source address. The more complicated extended access control list can base their decision whether to permit or deny based upon source address, destination address, port numbers. For example, we might allow port 80 and deny port 25 for email. But in this particular course, we're just looking at standard access control lists. So at the CCNA level, we used to teach Novell IPX and AppleTalk, but in the past few years, the feelings in the IT industry is just let's do everything over IP packets. So voice over IP, data over IP, video and voice over IP stuff. Let's do everything over IP packets, IP version 4, IP version 6, and let's get rid of all that old legacy stuff like Novell Network IPX and AppleTalk stuff. So access list controls are defined on a per protocol basis. So if I was only running IP version 4, I would just need the one access control list for the IP version 4 traffic, the source address. If I was running a dual stack operation where I'm running both IP version 4 and IP version 6, then I would define one access control list for the IP version 4 and another access control list for IP version 6. IP version 6 requires extended access control list code, so we're not going to cover that today. We're just going to look at plain old standard simple IP version 4 as our single protocol. Access control lists are one direction at a time on the interface. So I could define it on an inbound direction or an outbound direction. If I only can have one inbound on the interface port. So on this graphic at the top here, I can have one IP version 4 access control list in the inbound direction and one in an outbound direction. And on the interface on the right, one in the inbound and one in the outbound direction. Now normally you don't have to have 4. Normally one access control list on one of the ports in the inbound or outbound direction is sufficient to filter the traffic or control the traffic that we want to take place. But if you had multiple protocols, you could do that if it needed it, if the business needed it. So a group of statements, access control lists are groups of statements that define whether packets are to be accepted or rejected. We use the words permit and deny, either coming into an interface or leaving an interface. We're going to write up a list of permit and deny statements, and it's going to go through these in order, in numerical order from top to bottom. Once a statement is found that matches, the IP address matches the IP address that you specify in that statement, then either that packet is permitted or denied, and the rest of the statements on the list are not checked. Now, here's a very important concept. All access control lists end with an implicit deny all traffic by default. It's not visible. So this means that all access control lists must have at least a permit statement in them somewhere, because if they're all deny statements and there's no permit statements, all traffic would be denied. And there's a much easier way to deny all traffic on an interface, and that's just have a shutdown command. So don't forget about that implicit deny any at the end. And some of the slides he's going to use, the guy that wrote these slides is going to put that in to remind us how that works. So sequential logical order from the top down. Once there's a match, the rest of the statements are skipped. So if the condition matches true, that means that the IP address that was in that statement matches the source IP address that's in the packet that's being checked. Only one access control list per protocol per direction per interface. Implicit deny any at the end of every access list. Okay, another important point. Access control lists will not have any effect on traffic that came within the router. So if you were consoled into the router or telnetted into the router, and you did a ping or a telnet to some other location, even if there's an access control list on the interface that goes out, it doesn't affect it. Access control lists only affect traffic that come into the router from some interface and exit the router on some other interface. So we're going to just look at standard IP access lists. The only thing they can filter on is the source IP address. Extended access control lists can filter on lots of other things as well, but that's not our subject for today, just standard access control lists. So baby steps here, we're just going to look at the standard list first. So here's the syntax. 2 steps here. First of all, we're going to create an access list that says what's the IP address, and this can range from a single IP address of a single host machine to a part of a subnet to an entire subnet to everybody in the world. And we're going to create this access list statement that says either permit or deny, and then we're going to say what are the conditions of this. In other words, what IP addresses does this apply to, from a single host machine to as many machines as you want. Okay, once that step 1 has been completed and we defined our IP address, then step 2 is we need to take that IP access list and apply it to an interface port, like a fast Ethernet port or gigabit port or serial port in an inbound or outbound direction. So that way, any permit statement will be applied just to those packets passing through that specified port in an inbound or outbound direction. And that's going to determine what you need to filter. By default, there are a range of 1 to 99 numbered access control lists that we can use for standard IP. Standard IP is source address only. 1 second here, I'm just updating my attendance. We don't have to worry about extended IP or AppleTalk or Nobel IPX or anything like that. In this course, we're just concerned about standard IP access control lists. So range of 1 to 99, and that should be enough for most companies. If you needed more than 99 for some reason, they have created an extra range of numbers that you can have 700 or 800 more. And then later on, we're going to look at an alternative to using the numbered list, which is using a named list. So you can put a mnemonic name that makes sense, like web filter or incoming mail filter, something of that nature. Okay, let's see what's going on here. Here's our scenario. That guy outlined in red in the middle of the diagram, that's the manager of the sales department. He is the only one who's allowed to go to the rest of the company network and actually create traffic to and from the engineering department and to the administration department. All those other droids in the sales department, they are not allowed to create any traffic, and it would leave their network. Only the guy outlined in red, that 172.16.30.2, he's the manager of the sales department. Only his traffic can enter the router and go to the other networks. Okay, so that's the thing that the upper management is not technically, they don't know technical stuff. They'll simply say, we have a security reason here to only allow the manager of the sales department to create this traffic to the other departments, and we don't want anybody else in your department to be able to create any traffic to leave the stuff. We don't want them messing around on Facebook or anything like that. They only the manager of the sales department is going to be able to do this. Okay, so this is our task that upper management has given us that we need to do by actually writing the lines of code and putting them in the router. Okay, so let's look at this first line. On router B, we're going to put a line that says access list 10. And what does the 10 mean? Standard. 1 to 99, anything from 1 to 99 is a standard access control list. And let's permit that sales department head honcho guy, 172.16.30.2, let's permit him his traffic. So that's the list that says permit that. Now, don't forget that there's an implicit deny any at the end. So that means that if you create any traffic, if you're the head of the sales department and you create any traffic from your PC, the one outlined in red, all of your packets are going to have a source address of 172.16.30.2. And this will match this list. If you're at any of the other machines, any other computers that's in the sales department, you won't be 30.2. You'll be 30.3 or some other address. And you will not match that first line because you must be that address exactly. 30.2, exactly. Not 30.3, not 30.1. 30.2 is the only one that's allowed. So the implicit deny any says, if you're the sales manager, you match that first line. Processing stops and you are permitted. If you are not 30.2, let's say you're that other PC, 30.3, your traffic will flow into the router's port, the default gateway port for all the guys in the sales department. And the router will look at that source IP address and says, you're not 30.2. Well, you're going to be denied because there's this implicit deny any at the end. You are to be denied. You are not to be permitted. So this second line here, access list 10 deny 0.0.0.0, that's a 0.0.0.0 is kind of like a wildcard in networking. It's like delete star.star on a Windows computer. Star.star is a wildcard that says delete all the files. 0.0.0.0 is a wildcard in IP networking that says that matches all address. So the action of the implicit deny any at the end of the list, which is invisible, but he's typed it in here just for clarity, is I don't care what your address is, you're denied. So the actual guy who's permitted in red, the 30.2 workstation, he was already permitted. And for him, that second line, the deny line, is never reached. For everybody else who's not exactly that address, they're 30. something else, the first line doesn't match them. It skips to the second line, and their traffic is filtered. Their traffic is denied. Okay, this two-step procedure, you could define an access control list without putting it onto an interface, and we haven't shown that code yet. We're coming up on that. The access control list you define will have no effect at all whatsoever until you actually apply it to a router's interface in an inbound or outbound direction. So in this case, we could apply it to the Ethernet port in an inbound direction or the serial ports in an outbound direction. Because of the way that standard access control lists work, they're kind of clunky. We normally put it on the interface closest to the destination of the traffic because we don't want to inadvertently filter other traffic that we didn't want to do. So outbound traffic is traffic that's already been routed by the routers leaving the interface. Inbound traffic is traffic that's arriving on the interface, and it'll be routed by the router. So in this example, the sales department traffic all goes into their default gateway, that .1 address on router B, Ethernet 0. That's inbound traffic. Think of what happens in a router now. Traffic comes into the router. The traffic is, the router studies the packet and says, where is he supposed to go to? And he looks in his routing table to determine which interface should I send this packet out to get him one step closer to his destination. So it's more efficient if we can do an inbound access control list, because that way we can filter the traffic before it goes to the routing table lookup process. That's what takes all the resources of a router. He's got to go through all those lines in the routing table, and it could be thousands of lines to determine which outbound interface, exit interface it should be applied to. So it's better practice if we can filter it in the inbound direction, rather than have it go through the entire routing table lookup process, be assigned to one of the serial ports, and then dropping it. Okay, now we have we made the access control list at the top here, access list 10, permit 172.16.30.2. There's an implicit deny any at the end. And now we're going to apply it to an Ethernet port. We're going to go to interface Ethernet 0, and we're going to apply a line of code to it. So we could apply it to the serial ports in an outbound direction. In this case, he's gone to the serial port 0 and the serial port 1, and he's applied access group 10 in an outbound direction. That takes a lot of router processes, and that's not the best way to do it. And also, it's gonna, if we had done that, we would have inadvertently denied traffic from the administration department to the engineering department, because none of those people have that sales department manager's IP address. So all their traffic is denied as well. So you got to be careful when you apply access control list. Sure, it allowed the manager and blocked everybody else from the sales department, but it also inadvertently blocked everybody, engineering and administration, from talking to each other. So let's do it this way instead. Let's use an inbound access control list, which saves processing time on the router. And let's apply that access group 10 in an inbound direction to the incoming Ethernet port E0 on the router. And that way, only the sales manager's traffic will be able to leave the sales department. And it won't inadvertently block legitimate traffic between the administration department and the engineering department. Okay, now let's have another example. The manager of the sales department has decided that he and 3 of his trusted lieutenants are going to be able to leave the sales department. Maybe he says both him, not only him, but his 3 top guys will have the ability to say, go to the administration department server and enter sales orders into the server computer over there. The other guys in the sales department, no, they're still not trustworthy yet. They cannot leave it. So this is similar to the first example, except instead of 1 PC being permitted to leave the department, 4 PCs are going to be allowed to leave the department. Let's look at the code for what this would be. Remember before we had the first line, access list 10, permit the 30.2 guy? Now we're going to add 30.3, 30.4, and 30.5 to the list. So when 30.2 sends out a packet, he's matched by the first line. When 30.3 sends out a packet, he doesn't match the first line, it drops to the second line, and there's a match. When 30.4 or 30.5 send out their packets, they're not matched by the first and second line, they're matched by the third or fourth line. All the other people who do not have the address of .2 or .3 or .4 or .5, they are not matched. They will be denied by the implicit deny any at the end. And we use the same assignment to the Ethernet port in the inbound direction. If I decide I don't like an access control list, to remove it, most iOS commands can be reversed by repeating them and put no in front of it. So if I don't like the code I typed in for my access list, or I just want to remove it for some reason and give everybody access, I can say no access list 10, and that'll remove it from the iOS listing. You probably should go ahead and go to the interface and remove that statement IP access group 10 in with no IP access group 10 in to remove that as well, because they work in pairs. They won't, if you don't have both of them in a pair, nothing really happens. Okay, now we have the opposite scenario. Okay, the president of the company has hired his worthless nephew to come and work in the sales department. All the other guys in the sales department have now been fully trained, and they're able and authorized to enter service orders, product orders into the system that's over in the administration department, except the worthless nephew of the president. And he now has this workstation 172.16.30.0. So the president says, yeah, I'm sorry, my nephew's going to work here for the summer. He's worthless. All he does is go on Facebook. Just patch his computer so he can't get out on Facebook and do all that stuff. Everybody else in the sales department, they can continue to do their jobs. So now we have a reverse. Before we wanted to allow 30.2 to get out and nobody else. And now we have the reverse situation. We wanted to deny the worthless nephew to create any traffic at all within the company network to get to the rest of the network. So 30.2 is to be prohibited from leaving that router B sales subnetwork. Everybody else in the company in the sales department is permitted to be. And we're going to look at something about the any keyword. Okay, now before we said access list 10 permit 172.16.30.2 when it was just the department chair, department person, department chief to leave. Now we have the reverse situation. 172.16.30.2 now belongs to the president's worthless nephew, and he is not going to be allowed to create any bad traffic. So the first line says access list 10 deny that one PC, the address of the nephew's computer. The next line says permit anything. That's a shorthand before we use the 0.0.0.0, which was matched all addresses. So we can use the keyword any instead. It's easier to type than all those zeros and stuff. So let's look at the logic of these two lines. If you are the boss's nephew and you have the address 30.2, all your traffic is denied. If you have any other address, like 30.3 or 30.4, when it hits that first line, you won't be denied because you did not match exactly. The source address must match exactly. So it will drop to the second line, and the second line says, oh, you're permitted. So you can see where order is important here. We're going to see in the second slide here why order is important. And then we have our code at the bottom that applied it to the Ethernet port in the inbound direction. Now, what if I typed it in reverse order? Order matters. So let's say I put the permit statement first and the deny statement second. Well, the boss's worthless nephew, when he hit that first line, it says permit any IP address, and he has any IP address, and it would be permitted and processing would stop, and he would never be denied. So we must put things in the right order here for the desired action to take place, or you'll get unintended results, unexpected results if you don't do this otherwise. This would not be what we want to take place. Okay, I mentioned this a little bit earlier before. When an access list is applied to an inbound interface, like our example here, the packets are checked against the access list before they go to the routing table lookup process. Outbound access control list has to go through the entire routing table lookup process and then be permitted or denied, and that's less efficient. Now, let's see if what happens here, if a packet is denied by an access control list. We've talked about ICMP, Internet Control Message Protocol, echo request and echo reply for pings. If a packet is denied by a router, the router will send an Internet Control Message Protocol administratively prohibited back to the source of the machine that created this. Just so if there's any error interpreting code in the program, he can say, oh, you're being filtered by an access control list. Okay, here's some notes from Cisco. Traffic coming into the router is compared to access control list in the order. We talked about the order. If you add any new statements, they'll go to the end of the list. Oh, this is a problem. I want to generally fix the list. We're going to have to delete the list and use Notepad and punch in a new list. The router will keep looking until it finds a match. When it finds a line that matches, it will stop looking and do the permit or deny that was in that line that matched. If no matches are found in the list, the implicit deny any at the end takes effect. So for performance processing reasons, frequently hit entries should be at the top of the list. There's an implied deny for all traffic that's not permitted. So this means that all access control lists must have at least one permit statement in them somewhere, or all traffic is denied. And that's not what you want to do. That wastes too much of the processor capability of a router. You could do better with just doing the shutdown statement. Now, let's look at wildcard masks. A wildcard mask is a little bit different from a subnet mask. It's kind of a mirror image or a backwards subnet mask. So if you look at the address 172.16, the network 172.16, that's what in the legacy world we would call that, in the classical world, a class B address. And the default subnet mask for 172.16.0.0 is 255.255.0.0. Well, in a subnet mask, the ones tell us this is a network prefix, and the zeros tell us this is the host portion of the address. A wildcard mask says the zeros tell us this number must match exactly, and the ones, which is the 255s are all ones, tell us I don't care what those numbers are. So this is what we are used in wildcard mask and access control lists to say filter which addresses do we pay attention to. So it's like a subnet mask. It's a 32-bit quantity divided into 4 octets. It's paired with an IP address like a subnet mask. But the numbers 1 and 0 mean different things than they do in subnet masks. So wildcard mask have, he says, no functional relationship. I say they're kind of mirror images. They're inverses. They're backwards. Because typically if you look at the most common subnet mask in the world, 255.255.255.0, the corresponding wildcard mask is 0.0.0.255. So this is what we use our wildcard mask to zoom down to one individual PC or to a range of PCs or all the PCs in the network or even all the possible IP addresses in the entire world. Okay, so let's look at this statement here. Access list 1 permit 172.16.00. And what this means is the zeros, the 2 zeros means to match this statement, the first 2 octets must be 172.16. 0 means must match exactly in the wildcard mask. The last 2 octets of the wildcard mask, ones don't care. So what IP addresses is this line going to match and be permitted? Well, 172.16.anything.anything. Any possible address on that class B address is going to be permitted by this. So think of it like an inverse subnet mask. So let's look at it in binary. The 172.16 is written out in binary, and the 0.0.255 is written out in binary. We have 16 blue zeros and 16 red ones. The blue zeros must match exactly. The binary 172.16 must match exactly to match this statement. I don't care what your last two octets are. Just so long as your network prefix is 172.16, you match. So 0 means check. The zeros mean, those blue zeros mean, that binary pattern, 172.16, must be exactly that pattern. 172.15, 172.17, close, but no cigar. This is not horseshoes. They don't match. They will not be permitted. Only that one will be permitted. Let's use wildcard mask as an example here. We want router A to permit the entire sales network and just the engineering, chief of the engineering department to be able to go into the server that's in the administration department. So in other words, all the people in the sales department, I guess they got, summer's over, and they got rid of the boss's troublesome, worthless nephew, and they're back to normal operations here. So everybody in the sales network is allowed to go to the server in the administration network on the left and create sales orders on the computer. Only the boss of the engineering department, the chief of engineering, is able to do the same thing. All the other engineers, because we want to watch out for these engineers. Only the chief is able to do this stuff. So there's our business requirements. So let's look at this first access list 11. It's 1 through 99, so it's still a standard list. And he says permit 172.16.30.0, 0.0.0.255. Well, all those PCs in the sales department are /24s. Their normal subnet mask is 255.255.255.0. So the corresponding wildcard mask is the mirror image of that 0.0.0.255. So that line 1, access list 11, permit 172.16.30.0 space 0.0.0.255. That means if your IP address is 172.16.30. anything, I don't care what the fourth octet is, you are to be permitted. So that takes care of the business requirement that everybody in the sales department can communicate with the server over the admin building. Now let's look at the second line. Access list 11, permit 172.16.50.2, 0.0.0.0. Well, 50.2 is the IP address of the chief of the engineering department. The business requirement is only he can exit the network and go to the server in the admin department. So 0.0.0.0 means must match exactly. All 4 octets must match exactly. That second line will only match source packets that have the IP address of 172.16.50.2. And that means only that engineering chief guy who has that 50.2 address, only his traffic is to be permitted. So now we've taken care of everybody in the sales department and only the chief of the engineers to go out. And there's the binary equivalent that shows the same thing. Okay, now let's apply it to an interface. So we're going to, the best practice with standard access control list is we apply it as close as possible to the device being protected. We don't want to inadvertently block legitimate traffic from other devices. So in this case, he's gone to router A, which is the default gateway connection to the administration department where the business computer is for the whole company. And we're going to filter the traffic in an outbound direction from that Ethernet port to where that server is located. So IP access group 11 out to Ethernet 0 of router A will do this function, and he won't have an inadvertent process. So remember that implicit deny any at the end? Here it is written out in red, just to remind us. The first line, 172.16.30, everybody in the sales department is authorized. The second line, permit 172.16.50.2 only the engineering chief. The third line, all other traffic is denied. If you are not 172.16.30. anything, if you're not 172.16.50.2 specifically, you are to be denied. And that red line is what's at the end of every access control list, whether you put it in or not. It's an implicit one that's always there. So if we look at the wildcard masks, we can see here that the 0.0.0.0, what is your IP address? I don't care anything. The 255.255.255.255 means we're not going to check it. Any address you have, we ain't going to check it. You are denied. So that's what that implicit deny any at the end does. Now, it's really hard to type out all those numbers. 0.0.0.0 space 255.255.255.255. I've watched you guys fat finger these things in the labs. It's so easy to misplace a decimal point or forget a space, and then you get an error when you try to type in the line. So as a shorthand keyword, we're allowed to type in any. That's exactly the same as the 0.0.0.0 space 255.255.255.255, and it's much easier to type. So we can simply say deny any. And that's what the implicit deny any at the end means. All traffic that hasn't yet been specifically permitted is going to be denied. So in this case, we could have typed permit any. And remember that case where the boss still had the 30.2 workstation? I mean, the boss's troublesome, worthless nephew had the 30.2 workstation, and we denied him and we permitted everybody else. So instead of having to permit everybody else with all the zeros and 255s, we could have simply typed permit any. So the boss's nephew's traffic matches the 30.2. That's the first line. He is denied. And if he's not that specific address, oh, it's okay, he's permitted. Now, outbound access control lists. The problem with outbound access control lists is all the packets have to go through router A and go through the entire routing table lookup process and then be denied. But the problem is we sent all that traffic from all the other networks, and they went through router C, and they went through the serial line, and they went through router B, and they went through the serial link, and they went to router A, and then they were finally extinguished. So that wasted a lot of capacity of our backbone traffic. But that's a problem with standard access control lists. We have to put it there. Extended access control lists can fix this better. However, extended access control lists is going to be a subject of another time. Now I need to skip ahead to some slides because we're not going to cover the extended access control list. Okay, now let's say, look at the stop line here, access list 10 permit, and there's a particular IP address of 192.168.1.100, and the 0.0.0.0 means just that 1.100 address, not 99, not 101, just that one particular address, matches that list and needs to be permitted. So as a shorthand, instead of typing out all the zeros, you're permitted to type the word permit host 192.168.1.100. As a matter of fact, the iOS will even tolerate if you just type permit the individual IP address and you don't type the host and you don't type the zeros. He's kind of like Microsoft Windows will gussy up your bad code. He'll figure out you meant that one individual host, and it'll have the exact same effect. Okay, to verify access control lists, we can type the command show IP interface. And it'll show us inbound and outbound access control lists that have been set or have not been set. In this case, an inbound access control list was number 2, and the inbound access control list in the serial port was 101. We can also type the command show access lists, and we'll see them in there as well. You can also simply type show running config, and you can see the entire configuration of the whole device, including any access control list that you've typed in. So here we have an access control list 2 with a red bracket on it. That's a standard access control list, which is our subject for today. And the blue lines is a extended access control list, which we ain't gonna worry about right now. Okay, let's look at operations here. Here we have an access control list that's been applied to the Ethernet port in the inbound direction. So the packet flows into the router, and normally it would go straight. Normally it would go straight to the router table lookup process. But applying an access control list in the inbound direction means, first of all, before we allow it to be looked up, be processed and sent out, we got to check and see if it's authorized. So this is more efficient. This is a more efficient method because it nips the traffic in the bud before wasting all the routing table lookup process on the router, which is what consumes most of the CPU cycles and the resources in the router. Is going through all those lines in a routing table, which could be hundreds or thousands of lines. So if we can, we'd like to use inbound access control list to check it. If it's an outbound access control list, however, it's got to go through the entire routing table lookup process because that's the thing that determines which exit interface is supposed to be sent out of. Well, if that exit interface happens to have an access control list on it and it denies the traffic, we've really wasted a lot of the router's processes by doing an expensive lookup process and then denying the traffic. So if preferable, if you can get away with it, try to use inbound access control lists instead. So here's the standard syntax. Access control list, standard range of 1 to 99. It only filters on the source IP address. We can use a wildcard mask to say, is it just the network, or is it a subnetwork, or a whole classful network, or every possible address in the world? And we need to apply it to the port closest to the destination, because otherwise it's going to inadvertently block other traffic. If you want to remove the access control list and start all over again, just type no access list 10 or 11 or what it was and type it in all over again. Okay, extended list we're going to skip. So let me skip here. We're going to get that in a later course. Okay, named. We need to know about named. The thing of the numbers is, what does number 99 mean? What does number 20 mean? It has no meaning to me except the programmer that wrote it, the guy that configured it, and then after he slept, he'll forget what it means. So in programming, we use mnemonic names that makes sense, like database sorter or salary computation. We make up variable names that have meaning to us. So named access control lists are a means of, instead of having to use an arbitrary number like 1 to 99, why don't we just make up a name? And that way also, if we have a limitation with standard access control lists, we only have 798 of them that we can use. So we use a name that makes sense, and that way with names we can have more than 798 if we need them. Well, that's crazy. No one would ever have 798 simple access control lists. But the advantage of using the named is you can make up a name that makes sense instead of an arbitrary number that makes no sense to anybody whatsoever. And he talks about using a text editor. If an access control list has to be revised, normally we just delete it and we use Notepad and we rearrange the lines and put the right order and the right lines on them, and we paste it back into the router. So here's an example. Even though this is extended, the theory here is the same. I'm going to type the name from the global configuration mode, IP access list. And then since I'm not using numbers 1 to 99, or in this case 100 to 199 for an extended list, I have to tell it standard or extended. In this case, he put the word extended. And he gave the name server access. Oh, this makes sense. This is controlling access to the server. And then he has the prompt changes to configure extended named access control list. In our case, it would change this kind of big standard named access control list, and you would put in the exact same lines of code we already talked about. Put in some permits and a deny. And then you would apply it to an Ethernet port in an inbound, outbound direction. But instead of using access group 99, you would say access group server access, and you would apply it to that. So the syntax is from the prompt, type the name of the list, and then permit or deny, just like you would with a standard name numbered access control list. So in this case, he has a standard IP access list in red, IP access list standard, because we have to tell the standard extended, and he's given it the name internet filter. And he said permitting 10.1.1.1. That maybe that's the host machine, that only one that's allowed to go out to the internet. Everybody else is denied. And let's not look at the blue ones because that's the syntax that you aren't responsible yet. Okay, placement of ACLs. If it's a standard ACL, we need to place it as, since we cannot specify the destination address like we can for extended, we have to place it as close as possible to the destination, being protected against the boss's worthless nephew. That's not efficient because the traffic has to go through all these expensive least data lines and then get filtered. So if we use extended access control lists, we can put them as close as possible to the source of the boss's troublesome nephew and kill that traffic right away. So if he tries to go to Facebook, we can put the destination address of Facebook in there and filter that right away. But we don't have to worry about extended until a later course. So put it in the proper location according to the limitations of standard. It can make the network more efficient, but you're going to have to use extended lists for this. Gonna need to skip past some extended stuff. Okay, standard access control list cannot specify destination address, only the source address. So they have to be placed as close as possible to the destination as possible. If it's put too close to the source, when we saw that example before, it inadvertently blocked traffic between the engineering department and the administration building. It will deny the intended traffic, but it will also unintentionally deny other traffic that we need for our business process to take place. So placement is a very important consideration. So in this case, it would be better to use extended access control lists, but we're not doing that right now. Okay, let's look at firewalls. What's a firewall? Well, your home router has a firewall. It has some features that will protect traffic from coming back into your home network that wasn't traffic that you asked for. For example, when you open up a website, there's the TCP-SC-Cisco. Open the channel, and only traffic that comes back from that web server that matches those sequence and acknowledgement numbers that match, only that traffic will be allowed back in. So someone trying to break into your home system, they won't have the right numeric values, they won't be able to get in. So firewalls are a device we can put to protect bad stuff from the internet from coming into our company network, or maybe protect sensitive stuff on the inside of our network from escaping to the outside world. So access control lists can be used in routers. You can actually, with Cisco ISR integrated service routers, you can do some fairly sophisticated router functions. Hold on, I'm just checking that. So you can do some sophisticated, fairly medium stuff with Cisco routers, but normally companies that are would get a dedicated firewall appliance. Now Cisco makes ASA, firepower routers. There's other companies that are really big in the firewall scheme. Tarrant County College uses Palo Alto firewalls, which are probably the best in the business. If you ask the IT department, they won't tell you, but if you go to the recordings of the public recordings of the board of directors, you can see, oh, they approved the funds for the purchase of Palo Alto firewalls. And Palo Alto is an Israeli company, and we all know that the Israelis make the best software. Another company, Checkpoint, firewall company, they're another Israeli company. So firewalls are positioned so that they can filter traffic inside and outside of the company. Okay, here's an example of something that all internet service providers do. That private inside address that you use at home, like 192.168.1.1, or the private addresses we use inside our Tarrant County College classrooms, 10.144. whatever what we use in the classroom, or if you come in and use our public Wi-Fi, that's 172.16. Those are all classified as private inside addresses. They're not allowed to be routed on the internet, because if they were, someone could, from the outside world, could create a packet with a source address of 10.144 and pretend to be in the business department building and try to sneak in. So all internet-based routers, all internet service providers have access lists that deny traffic that are these addresses that shouldn't be out there, like the 10. The Class A private inside address, 172.16, 192.168. These are denied, so that bad guys from the outside world can't try to break into the company through your internet service provider link. Okay, one more thing to cover, and then I'm going to go and show you how to set up a lab for this particular chapter. There is a special variation of access control lists that add an extra level of security to when the authorized IT guys, they want a telnet or secure shell into a router or switch. Now, normally we protect them with a password. Like we put a line that says line VTY04, password Cisco login. So you have to know the password Cisco to be able to log into the router. But this adds an extra level of security. What we can do with the access control list is, in this particular example, let's say that the IT guys in the IT department are all having network addresses that are 172.16.1. something, or 172.16.2. something. They're the only ones that should even attempt to type in the correct password to get into the router. So we can create this access control list that says only the .1 and .2 guys are allowed, everybody else is denied. And then on that line VTY04, login, password Cisco, we add another line that says access class 2 in, and that way, you can't even attempt to telnet in or to secure shell into the router unless your source address is 172.16.1 or .2. And that adds an additional layer of security. Now, security is like layers of an onion. We want to do as many different things as possible. So if the bad guy gets through one layer, maybe the other layer will stop him. So again, standard and extended access control list only apply to packets traveling through the router. So if I was consoled into that router, if there was an access control list, it wouldn't pay any attention to it. It would escape the router and go wherever it was supposed to go. So an outbound telnet list wouldn't prevent router-initiated telnet sessions, for example. Okay, guys, stand by 1 second here. I'm going to put this one away. I'm going to bring up the packet tracer. And let me see. First of all, I want to show you a picture of the lab we're going to work on today. Okay, this is kind of more complicated than some of our previous labs. We have 3 routers connected together. There's a couple of gotchas in packet tracer I'm going to show you to get around here. First of all is creating and connecting the serial ports. There's no serial ports on these routers by default. We have to provision them and turn the router off and on. I'll show you how to do that. And there's quite a few devices in this scenario. I'm going to set up this lab topology and use my best practice of show Cisco discovery protocol to make sure that everything's connected properly from the guy in the middle, the router at the top of the triangle, the ISP router, and then I'm going to cut you guys loose and you can do the labs on your own. Okay, so here's the picture of it. I'm going to put that away. I'm going to put up packet tracer. And I had to make it a little taller because there's so many devices in this particular lab. Okay, so the first thing I'm going to do is I'm going to bring these routers into position, R1, R2, and R3. And in this particular lab, it's the 1941 routers with gigabit 0/1, just 2 numbers on those. Okay, so I'm going to click on the, I got to go to the real thing here. There we go. My mouse is floating around. Good. All right, so I'm going to put in a router at the top and a router to the left. And I kind of squash them together here because we don't got much real estate today. Okay, I'm going to do the things I normally like to do, which is I'm going to go to the router 0 at the top. And I'm going to go to the configure tab. And I'm going to say that router name is going to be ISP. And notice at the bottom of the screen here, he goes ahead, he types in the code to do the host name for me. Normally I have to type that by hand. Now I need to, let's go to the physical screen and look at this router. Oh, look, the router has got 2 Ethernet ports and doesn't have any serial ports. Remember in our lab, we have serial ports over here. We have a little 4-port switch over here. Okay, I need to apply this serial port over here. Here's the serial port. But I can't put it over there because the power is not on. You cannot add module when the power is on. Okay, all right, then I'll put my little mouse over here and I'm going to turn off the power. Oh, good, the power went off. The green light vanished. Now, just like on a real router, you have to turn the power off when you plug in the new option card. Now I'll turn the router back on. And it's booting up. What a bunch of nonsense. But that's what we got to do in the real world, and they pretty much realistically duplicate that in the Cisco world. Okay, great. Now I'm going to do that also for the other 2 routers because they have to connect together with serial ports. And out of the box, if you look at this router, he has no serial ports. Well, let's look at the one we provisioned. Yeah, he's got 2 Ethernet ports and 2 serial ports now. I need to do that thing for the other 2 routers as well. Okay, so I'm going to go to router 1, do the configuration, make him R1. He'll punch in the host name for me. Then I'll go to the physical side. I'm going to turn off the power. I'm going to drag the serial ports over. I'll turn the power back on. Yeah, he's booted up. Good. Okay, now let's go to the 3rd router, R3. I'll go to the physical side, turn off the power, drag the serial port, plug it in, turn the power back on. Then I'm going to go, oh, he's booting up. All right, let's wait for him to boot up here. I need to change the host name. So that one on the right is router R3, router R3. He punches the host name in for me. Great. Okay, let's go ahead and connect those serial ports together now. And then we can do the other connections with the switches and the host PCs. So I'm going to click on the jagged lightning bolt thing. And instead of using the solid Ethernet cable, I need to use serial cables. Now you can use either one of these red ones. I'm going to just use this one. So I'm going to click on router 3, and the diagram on the front page of the lab says the 001 port of router 3. Oh, I named it router #. I need to correct that. Goes back to the 0001 port on here. Let me fix my typographical error here. That should be router 3, not #. I was holding on to shift key or something. Okay, now I'm going to click on the serial port once more, and I'm going to connect router R1 000 port to the 000 port of the ISP router in the middle. Okay, those connections are made up now. Okay, good. Now we can do our normal Ethernet stuff we're already used to. So I'm going to go back and drag a couple of switches in the topology, S1 and S2. So S2, I'm going to make him S2 instead of the default name. S2. He'll punch in that CLI for me. And I'll go to the switch 1. Oh, I'm sorry, he's supposed to be S3. S1, S1. Now switch 3. It's supposed to be switch 3. I made him, oops, wrong device. Okay, it's S3, not S2. Okay, let's clear up some space here because we need to grab a couple of host machine PCs into here. So I'll click on the PCs, and PC-A will be this guy, and PC-B will be this guy. And I'll go into the configuration screen and correct the names so that they look nice on the screen. So this one is PC-A. And the one on the right is going to be PC-C. Okay, let's do our normal Ethernet connections now and connect all these guys together. So I'll click on the connection screen, bring up a standard Ethernet cable, and PC-A Ethernet plug is plugged into port number 6 of the Ethernet switch that he's connected to. PC-C, his Ethernet plug, is plugged into port number 18. And then port 5 of each switch connects to the G01 port of each device. G01 goes to port number 5. The lights are red right now on the switches. They'll come up in a few seconds as the PCs come up. The lights will remain red on the Ethernet ports of the routers because the default state of the routers is they're all in a no shutdown condition. I'm going to go ahead and go into the routers and simply do a no shutdown on all the ports, and I'm not going to assign any IP addresses, and show you how we can check for proper wiring from the router in the middle ISP to make sure that we have a connection. So I'll go to router R1, and let's go to the command line interface of this. So go to the privileged exec mode, go to the configuration mode, host name R1, and that port interface G0/1, I'm just going to do a shutdown. And that other port, interface S0/0/0, I'm going to do no shutdown here too. I don't need to apply any IP addresses at all yet. Okay, so I've given the host name. Let's go to the router in the middle, ISP. Do a similar thing on him. Okay, go to the privileged exec mode, go to the global configuration mode, host name ISP, and go to the interface S0/0/0 and do a no shutdown, and then go to interface S001 and do a no shutdown for him. No IP addresses required whatsoever. And then I'll go to router R3, go to CLI. And let's go to interface S0/0/1, do a no shutdown, and then go to interface gigabit 0/1 and do a no shutdown. And that should clear up all those lights. After a few seconds, we should get greens on all those lights. Okay, good. We have pretty much green lights here. It looks like there's still waiting for R3 to come up and up. Take a few seconds for that. So if we look at R3, he's telling us that the gigabit 01 is up and the serial 001 is up, going back to the top of the triangle ISP. That's fine, that's fine. Go to ISP. He tells us that the serials are all up and up. Though there's no Ethernet ports being used on ISP. You're going to use a loopback port on that one. Okay, here's the big test. Now, Cisco Discovery Protocol is the protocol that will look over that with just data link connections. We brought up good data link connections. We didn't apply any IP addresses yet. We should be able to see our neighbors. So if I look at R1, what's directly connected to R1? S1 and ISP. Okay, it only shows you directly connected neighbors. So I'm going to do a show CDP neighbor, and I can see that I'm connected to S1 and ISP. Good, that proves that connection's good. Let's go to the ISP router. And this is particularly great in the lab when you wire stuff up in the lab. It's kind of hard to see if you swap wires. It's pretty easy to see in Packet Tracer. You can check and see before you make a bunch of mistakes. So I'm going to show CDP neighbor, and the router at the top, ISP, his serial 001 is connected to the 001 of R3. That's what we're supposed to be. Router ISP's serial 00 connection is connected to the 000 of R1. That connection looks great. And lastly, let's go to R3 and check him. He should see ISP up to the left, and he should see the switch down below him. Show CDP neighbors, and we can see that he is connected to switch S3 at his gigabit 01 port to the port 5 on the switch itself. This is very cute because it tells you not only your local interface, but the interface on the other side of the wire. So it's real good for troubleshooting if you're not sure how things are connected together. Okay, so that's the setup of the topology for this lab, and the rest, as they say, will be left as an exercise to the student. So I'm going to go ahead and say thanks for coming, guys. Nice to see you today. I look forward to visiting with you next time. And I'm going to go ahead and mute my mic and say adios and log off for today.